list of contributors to our multiphysics project for C. And so we started really from from one center, so one institute in Munich. So they are our main contributors, and then expanded to the Bundeswehr University of Munich, further then to Herion, where I'm working at, and Colonia, Stuttgart, and Bochum. So there, the whole stuff is spreading step by step what we're doing. But let me first give a small introduction. What is our code project? What can we do? What might be interesting for you? And then what the session name tells us, give a little bit about what did we learn during our last years, because it is a quite large project, and in the end a small summary. So it's mainly about multiphysics, and it's quite old code, so development more than 20 years, quite large, more than 1 million lines of code, and many publication and PhD theses have gone into this code project. Here on the left side you can see our single fields. So it is possible to run a single field also, of course, so solid, fluid. Fluid includes maybe some turbulence models, scalar transport, might be temperature, might be some concentration that is evolving over time. So this is up to you what you're interested in. And when we're talking about the structures, this is mainly about 1D beam formulations, which are then interesting to be coupled with other fields. So on the right side, there's a small, really small overview what is possible. So it's, for example, a human lung that has been simulated in the meanwhile. So it's about the flow that is entering the lung and it's expanding. So this is the solid part. Some poro-elastic interaction is included in there. And also what is shown here, this is maybe an injured area of the lung. So there we can even plug in, so to say, in the multi-scale approach, a second discretization, a second model, which then gives detailed analysis of that region, which goes back into the macro model. This next one here is maybe something like a one-sided valve, so the flow can enter in that direction, but not in the other direction. So it's about contact of the structures, and the fluid flow drives the whole thing. Here, the next one on the right side, this is, as I mentioned, with the beams. So flow is going through these beams. So this might be seagrass that is underwater. And what about this interaction? So how does the structure, this beam or this grass, influence the fluid and vice versa? Then this here on the bottom, this is a battery that is simulated. So it's about the concentrations during the charging process. So it's heated, that battery, during this charging process, and also somehow expanding. So here again, this multiphysics aspect that is considered. Next one is quite obvious, it's just a tire. And so a quite new part that is included in our code project. It's about additive manufacturing. So it's about the melting, the resolidification of the whole stuff, and how this powder bed starts in the beginning and is moving around. So if I may briefly summarize the goals that we have, it's about multiphysics mainly, but of course you can run the single fields too. It's about really analyzing real-world problems. You've seen the geometries, so this is far beyond the unit cube that might be used for methods development. And of course, because these systems are usually quite large, it's about also efficient use of HPC systems. So here, do not use the standard solver. It's about multi-grid solvers that are in use, really to make an efficient use of what is available at the computing centers. And if we may cluster this a little bit, so it's in science, it's in engineering, it's in biomedicine, these are our three big areas where we are working on. And what I think is very special is the biomedicine application, because it's really about the brain, the lung, stomach, some muscles, some tumors. So all these parts of the human body have already been simulated successfully. But now let's get to the RSE aspect, and because the session is named Lessons Learned, so let me come to this point. So here a little bit about the history that we had. So start was beginning of the 2000s. The code was developed by roughly 10 people. It was based on Trilinus National Labs US project. And from This we use the linear sparse algebra and the solvers, but the remaining stuff is developed by our own. And what is very important, this is this policy here, all the development should happen within one code. So over these almost two decades, all the people have contributed into this single project, and that's the reason why we had a really good chance to set up all these multiphysics couplings, because everyone contributed a little bit, and in the end we had really a chance to couple many, many different things. But then the interesting aspect comes, so this is just an overview, I'll go into detail in the next slides. 2 side projects on the bottom here have been launched, and this main code development, this is so to say the central line and the upper part, but I will go into detail in the next slides. So let's just have a brief look at these 2 side projects. So one is XRDG, it's fluid solver. It focuses on large area simulation and direct numerical simulation. So really a detailed view on the fluid. And it is a really fast solver. So it uses matrix-free operator evaluations, which makes it very suitable for large systems. And it's based on DL2 and finite element library for HPC systems. And it really started with a single person. On the right side, this is our Trixie particles. It's a Julia code. It focuses on particle-based methods. And you can see, oh, perfect. Thanks, the video runs. That's good. So you can see some here SPH simulations that are done with it. And the interesting part is, why did we launch these side projects, although we have such a big main code actually? And it was always the problem that what was desired from these, with the side projects was reached, it was just too far away from what our main code could provide. So single person, 2 person started, but they did not start from scratch. They really set up on an already existing strong framework. This is on the one hand here the DL2 library, or the Julia framework is mighty in itself. So this was then for both projects a really good start, and what we saw and learned from that is both projects, they make really fast progress. So meanwhile 6 and 8 persons are working on these 2 projects. They have a very clean state, so that's really good. But what we also recognized is we lose this connection to our main project. So in the past it was always the case, when we have something new, just couple in, perfect, that's it. Here we now have really the challenge to, let's say, efficiently couple them. So we can couple them, of course, in some partitioned manner and going back and forth between the solvers, but this is not something that is that efficient. So here we're still struggling and still working on that part, although we expected this to be a little bit easier. Now let's get back to the main code. There we also learned a lot of things. So what was the starting point in, let's say, something around 2019? We found that our project is meanwhile so large that it's really hard to maintain. It was developed by mainly PhD theses, and the people are better or not that good in writing code. And the whole concepts, they just came to their limits. So we had some pressure to start with something new. So what did we do? The plan was, let's have a new code set up based on DL2, and what is shown here in this middle, let's phase out the old one and phase in the new one, such that in the end all the people are sitting on the new code, and let's continue development there. But let me get to the next slides, because it didn't happen as we planned. We had some chicken egg problems, so to say. The new code, it was not yet ready for the transition of all of the people, because the main ingredients were just in the old code, and people said, oh, it's difficult for me, I'd like to do my research, I'd like to publish things. I have there the strong code, why should I use the new one? And so we had roughly 2 people, 1.5 people exclusively working on this new code. And it was always more code produced in the old framework than in the new one. So this plan was, let's say, 1.5, 2 years of having the transition. And what happened after 3 years, there was still no full transition. So this was really a challenge. And I would say it was really the lack of dedicated RSE engineers that should have focused on setting up fast this new framework. If we would have, let's say, 2 to 3 people doing this intensively, I would say we would have had a chance to do so. But this was not the case. So what did we do? We put this successor development on hold and started an intensive refactoring in the old code. This was interesting because we learned a lot by setting up this new code. So this is now really a good prototype. And based on what we learned there, we started to do our refactoring and having a clear set in mind where we'd like to go. So this was not really a waste of time. It was really interesting to do this because we learned a lot by doing so. And now it's also possible to include more or less all the people. We created some task forces and assigned all the developers to those, and they can now contribute in their field, their part of the code, and this helps us a lot. And what did we do? It's mainly about the dependencies, so internal as external dependencies that we cleared. Internal means we have now one physics agnostic core module, and the physics modules, so the single fields that we have, they're way more structured now. So this helps us especially for future development. The external dependencies, this is just about which libraries are we using, which versions of them. We put everything into a Docker container meanwhile. And the code modernization, it's about, we use now modern CMake. This was a good step. And yeah, the fields are just cleaned up, some parts are templated. So here we made really good progress, but always having this set in mind where we'd like to go. And what did we achieve by doing so? So it's way more robust, especially the testing aspect. So within our CI pipelines, this works now way better than in the past because we're really aware of what is necessary. If we change to another system, that's way better doable. To some extent, it's already portable. So if there's a switch in, for example, our Ubuntu version, there's not really a problem now. So it goes way better. And the code itself, it's way more understandable. So that's really helpful, especially for our future research that we're actually interested in, because this is something we need to do. But what we're actually interested, of course, is what can be published and what can be found out or to find out in our research. And what is very interesting or important to us when we look at our FAIR principle is exactly the I that we're mostly interested in, because we're already good in doing a couple of things. But when we think about our side projects, we somehow lose this connection. And here we need to do another step and make this interoperable with our old stuff, not old stuff, but our refactored main stuff. So here, this is still ongoing work, such that we get them back into our whole framework, because then I'm convinced we will really profit from that, because then we have new, challenging, good things that a big backbone, the old one, and this will allow us really, really good research, I'm convinced. So what did we learn out of that? We had the plan to set up on a good finite element backend library such as DL2, but it was really, really difficult for us to get there because it was just having more people working on the old than in the new. So for us, it turned out that this refactoring is more feasible for us. So the hope was, of course, it should be the other way around. But at the end, we're now at this point. But we're somehow actually happy because this refactoring, it revealed all these fragile code parts and revealed our technical depth. So we now know where to have a look at. And due to this usage of modern tools, such as the deRSE24 or ClangTidy, and modern CMake. So these tools, they helped us a lot to have good progress here. In the end, for me, it remains still the question, what would have been faster, going to this completely new one based on DL2, or having now our refactored version. So both takes a lot of time, so I can't give a definite answer there, but it's really hard to assess, I would say. We, of course, do also some community building. Here's a photo of our group. So we had a nice meeting last year in Bavaria. And it was really an RSE event, so to say. It was not about research. It was about discussing sustainable coding. How can we get our things done? How to structure our refactoring. So this was quite interesting. And this September, there will be another one. And if I'd like to summarize the whole thing, I would say we have a challenge with our old code. We tried set it up new, then changed to a refactored version because it is more feasible for our group, for our maintenance, or for our staff that we have available. We have launched side projects which are very successful, and the challenge is really couple them back to the main code, and we'll publish our code for C this year. So here currently, or still the old name is in use because we decided for publishing that we will change the name. So the original name is deRSE. We will publish it under the name for C. And if you have a look at our webpage, you'll find all the publications. Have a look, and then feel free to use the whole thing. So you can either use it as it is, run some simulations, what you've seen, or you can also extend the whole thing for the needs that you have. So thanks a lot for your attention, and I'm open for questions. Thanks.